Okay, so thanks everyone. And so my goal with this little tutorial is kind of threefold. As we go around designing and deploying mHealth systems, kind of things to keep in mind when it comes to security. Whenever we think of mHealth and sensors and things like that, it's kind of the thing in the background that will the data leak, all those kind of issues which come up. Of course, we're all used to IRBs and things like that, but I think these systems present challenges which I think even most of the IRBs are clueless about. So I've kind of touched upon three things. One is technology that currently exists and for which where there is no excuse not to adopt. So what sort of the best practices are. This institution had a big breach just a couple of weeks ago, or at least reported a few weeks ago, which falls under that category. Secondly, things which are happening in the sense that over the next few years, they will become practical. Right now, they are in computer science research sort of level. And then finally, touching upon things which really a general guidance about that as you go around collecting the data, how to organize these things from a security perspective. So when we think of mHealth, it's much more than just the app, obviously. It's kind of the entire flow of data through multiple stakeholders, kind of third-party services, your data may be touching some cloud services and eventually reaches the researchers or patients or doctors or whatnot and all, right? So kind of an end-to-end data flow which happens. And throughout this, there are all sorts of vulnerabilities. Some of them fall under the category of just incompetence, laziness, even though the technology may exist. Some of them are new, things like now these are systems which are not just cyber systems, there's a strong physical element. Santosh talked about sensors yesterday, for example. So these things are physically manipulatable, and unfortunately that creates another attack vector on these things. And then there is this whole issue of that you can secure the system, but then authorized users can misuse it. There are plenty of examples of so-called insider attacks where sort of personnel in the hospital, for example, snoop at records and things like that. So that unauthorized use by otherwise authorized users. Now, no system can be designed to be completely secure. So one way security professionals like to think of it is that your overall risk, the probability that something bad will happen, is really a function of three things: the threats, and unfortunately, we have a lot of new threats which are emerging. Okay, I mean, people just trying to hack into systems for fun, for example. Vulnerabilities, these are the weaknesses. Sometimes these are human, sometimes these are bugs, sometimes we just don't know how to protect against them. And finally, obviously, the impact, that is it worth protecting? What would be the damage to the assets? So traditionally, computer security organizes these concerns around a bunch of different goals, and different parties have sort of different attach different values to these goals. So if you're conducting a study, obviously availability of the data, availability of the system becomes important. Authentication, confidentiality, quite important for the person whose data it is. Integrity of the data, regulating sort of the use of your system, being able to audit. This is something Ida had touched upon, kind of this notion of provenance, that when things go wrong, being able to kind of diagnose forensic part of it. And then finally, kind of another non-repudiation, which is that the sender and receiver, they cannot back out. So this happens in, let's say, in a banking setting and things like that. And there are various ways to achieve it. Not all of them are computer science related. A lot of these things are about having good policies in place, for example, or doing background checks on the people involved, those kind of things. Now, of course, during this talk, I'm going to focus more on specifically computing, the role that computing plays in this. So to give you a sense of what the current state of practice is, some things are essentially solved. They may not get deployed correctly, and that's the human element. So for example, confidentiality from authorized users, whether your data is in motion, passing through a network, for example, or a stationary on a mobile device on a server. It's a solved problem. Very strong mechanisms, encryption-based, available. Again, they may not get deployed, which is kind of the practice story. Ability to authenticate. Again, solve for most common cases, particularly those of you, for example, the newer generation phones with combination of fingerprints and passwords and things like that. These are systems which, if deployed correctly, are pretty good. And I'll talk about this notion of certificates and digital signatures, which actually, unbeknownst to you, you're sort of all using, and which is how you trust when you go to, for example, Amazon.com, that you're indeed going to Amazon.com. This notion of pairing sensors with our devices, again, very robust. We routinely do it with our Bluetooth sensors and all, so our sensors don't talk mistakenly to a nearby phone, for example. And tampering with the platform. So again, ignoring the issue of bugs, which unfortunately, these are very complicated systems, will never get eliminated. But for example, on our phones and newer computers, there is this little piece of hardware called trusted processing module. And what it does is it makes sure that the operating system that you have on this platform is coming indeed from Apple or Microsoft, and then a whole sort of chain of trust gets built on it. Bottom line, these things are at least in a technology sense solved, but there is a set of problems which are very hard. So for example, mHealth systems rely quite a bit on services in the cloud, and this is often a debate between should we sort of send things out or not. For example, in our MD2K center, we have sort of taken a more conservative approach. All servers are in-house, but the reality and economics is that these things are going to be increasingly touching other service providers who you may not entirely trust. So could we offload computation? Could we do large-scale machine learning out in the cloud while still essentially having same level of security as if it was a server inside a physical barrier? Unauthorized use by authorized users. This is a real challenge, and particularly as I'll show, sensor data, unfortunately, you can make lots of different inferences from it. So even something as simple as accelerometer, for example, while maybe useful for stress, there is a zillion other things that you can infer from that. And so while as a researcher or a medical professional, you might think that, hey, I'm not going to misuse it, the issue is if the data is residing unprotected, or think from the perspective of the person who's contributing the data, as the knowledge about these risks go up, the degree to which they will consent to participate will be affected. And then finally, physical attack vectors. So these bottom three rows kind of represent where a lot of current interest resides in terms of coming up with solutions. Now, the challenge which comes in this is that there are many stakeholders, and obviously their interests are not aligned. So for example, patient obviously cares about confidentiality. On the way right, researchers care about confidentiality, but really under the threat of liability. Patients worry about quality of service, whereas quality of data, kind of having all the raw data, for example, is a natural instinct of someone on the right. Services in the middle worry more about efficiencies, uptime, scalability, sort of essentially economic considerations. So the challenge often comes is to kind of strike the right balance between the interest of these kind of stakeholders. Now, the magic behind the current technology really rests on a very few technologies. So one is this notion of symmetric encryption, and without going into details, essentially it means that we share a secret using secret key. I encrypt my document, data, sensor data, whatnot with it, and I hand over to you. You have the same key, a copy of the same key, you can decrypt it. Now, as you might imagine, the problem with this is that how do we go around securely distributing these keys? Someone steals them, we have a problem. So to the rescue came something called asymmetric encryption. It basically says, my lock has two keys. They're different, but they're coupled. You can lock with one key and unlock with the other, or vice versa. And that turns out played a very important role in development of security technologies, which basically lets us then use these asymmetric encryption to then generate shared secrets and then do very efficient symmetric encryption. So this is routinely used by computers. And then finally, there is this notion of cryptographic hashing, which basically say, I can take large amounts of data and then reduce it to a very small number of bits, which kind of act as a signature for this large amount of data. And it has some nice properties that, given that signature, you cannot recreate the data. Kind of stands to reason, you're going from many bits to fewer bits. But more importantly, if you perturb your sensor data or document a teeny bit, the signature is going to be totally different. Okay, it's very hard to kind of spoof this mechanism. So this is how, for example, digitally signing documents or verifying that the software or data you're downloading is indeed what it is, these things work. Now, surrounding this is something which in recent years has emerged, and that is the so-called public key infrastructure and digital certificates. Very crudely put, digital certificate is a file in which is a public key for you. So remember, I talked about asymmetric encryption. The two keys are referred to public key, private key. So whenever I have an asymmetric encryption, that I'll generate a pair of key. One I will keep with me, the other I'll advertise. And in this particular case, that public key, if someone says that, look, this is my public key, how do I know it indeed is that person's public key? Amazon, when our software talks to Amazon or Google, then we need to trust the other party. So these companies publish their public keys, but then we need to know indeed who they are. So there are these other companies like VeriSign and Symantec and a bunch of these other companies. What they do is they act as certificate authorities. Essentially, they are the source of trust. And what they do is, using the same cryptographic primitives, they sign these things. So your browser, your software, they all have these digital certificate files, and sometimes you may see this message popping up, unknown certificate and all. What's happening is your browser is suspecting that the party is not what they are claiming. So between these two sets of techniques, kind of the basic crypto mechanisms from the previous and these digital certificates and this web of trust which exists commercially, at this stage we can basically protect data. We can know with fair assurance that Wells Fargo is what they claim to be and things like that, and therefore conduct secure exchange of data. So for example, you stitch these things together and you can have your app talk to cloud services, trusting that the cloud service provider is indeed what they are, and your data is sort of essentially foolproof, secured along the way. And now, of course, all of these things are affected by existence of bugs, existence of NSA, things like that. So ignoring those issues, which are the political realities and complexity, but that's where it is. So current encryption, as I said, is extremely strong if properly deployed. The problem is it's extremely inflexible. So if I encrypt the data, you have to decrypt before using it. So let's imagine on the phone I collected some sensor data, and now you need to do some big computation on it. So you want to farm it onto, let's say, one of these machine learning cloud services that have emerged. The problem is that we don't really know how to do it without decrypting it. The problem with decrypting is the moment I decrypt, of course, whoever has a copy gets to know that. So for example, in this case, let's say a user on the left, it could be a researcher with lots of data trying to use some commercial service. So it has X, it needs to compute f of X. The ability to compute f of X is in this remote place. So if I just send X as is, of course, the other party learns X, so I can't do that. So decryption currently, encryption, decryption is really all or nothing. We can't really control that process. So a very common scenario that happens is that there may be an end user, there may be some sort of a party in the middle, and then the eventual researcher or other consumers that may exist on the right-hand side. And you might say, okay, fine, so I have my sensor data, I'll send it to this database out there, and I'm going to send it encrypted. But now, of course, the researcher or as the external party, they need to query it. They need to do some computation of it. So that's what I've listed as f of x, g of x. So I have really two choices. I can do the computation myself. I can ask the computation to be done by that middle party, but then I'm revealing the data, the private data, to that middle party. Or alternatively, I can send the encrypted data all the way to the end user, but then I have to give them the key and they get to know the raw data. So neither one of them is satisfactory. So what's happening in recent sort of 10 years or so is some new powerful forms of encryptions have emerged. So one is something called functional encryption, which actually came out of one of my colleagues out here in computer science, Amit Sahai. So what it does in effect is the following. It encrypts the data, but then hands out keys, which when you apply to that encrypted data, you actually, instead of getting the raw data back, you get a specific function of it back. So I can basically say, okay, I can publicly post the encrypted data, and let's say you want to know f of x, some function about that data, I'll give you a key which will only give you f of x and nothing more. So that's great because I can literally kind of just keep the data secure and then reveal or share on a selective basis. So you can do things like a particular stress event is only exposed to if the user is from UCLA and is a faculty, or is anyone from Memphis, or things like that. Even more powerful is this emerging notion of class of encryption techniques called homomorphic encryption. And they go back to this problem which we often face, that I want to use a computer, a remote server, which I may not fully trust, but I want it to do the computation because maybe it's cheap, it has lots of computing power and things like that. It's commercial service. So I have x, I want to do f of x, and as I said, we cannot simply send x because then I'm revealing the private data. So it turns out homomorphic encryption basically lets you do computation over encrypted data. So I can send encrypted x, and then the remote party will just do the computation on it as if it was unencrypted. It will just go ahead and apply that function. And then when it comes back, it basically relies on the fact that computation and encryption are commutative. I can reverse the order whichever way, and it kind of works fine. The breakthrough in this thing came a few years ago by a researcher out of IBM, which basically showed that this can be done for arbitrary computation. So rapidly improving technology. And just to sort of give you a sense of that, I'm going to jump ahead one slide actually. A recent work out of MIT showed that machine learning classifiers, which we routinely use in mHealth, can be done very efficiently with this kind of approach, where they basically, you can farm it out to a server. In fact, they go even further. Not only is the data kept private from the researcher or the consumer, but your algorithm is kept private from the client also. So your model bit, which is often proprietary, is also kept. And the results show that this thing can be done quite efficiently. Of course, not as efficiently as doing it on kind of unencrypted data, but sufficiently so that it becomes sort of in the realm of possibility. Another, a third technique which is emerging quite a bit is this notion of secure multi-party computation. So this, for example, may happen, let's say there are a bunch of centers which have collected data, and now you as a researcher want to analyze that data. Of course, one approach is that every center agrees to hand you the unencrypted data, you do your computation on that. Or alternatively, could we do this computation without knowing anything more about that data other than, of course, the result of the computation? And it turns out, again, that can be done. So now one solution here is a so-called God solution, which we say, look, we designate a third party which we all trust that they will keep the data, maintain privacy and do the computation. But of course, that's unrealistic. So what SMC protocols do is they basically make sure that even if some of the participants may be nefarious, they may collude and all, through the appropriate design of these secure protocols, we can do this magic. So we can fuse data across different studies, for example, in a secure fashion. Again, current state, these things exist. They are not as efficient as, for example, the GOT solution in terms of sheer computing power, but Bitcoin, which I'm sure all of you have heard of, relies on this, for example. So this is technology which is kind of out there to adopt. So secure processing and selective sharing, these are kind of the two things which are on the cusp of getting real. Question then becomes, what should we share, right? I mean, so that goes to this issue of unauthorized use by authorized users. And that really boils down to fundamentally an issue of trust, the value you derive from sharing, and the risk you are taking by sharing. And that's at the heart of the privacy problem. All these three things kind of matter. Now, the issue out here is that mHealth systems, really, given that they rely on all these sensors, are really sort of giving you very intimate running time series of your personal activities, and that's what makes us feel creepy about these kind of things, or at least many of us. Problem fundamentally is that there are lots of unexpected inferences that can be made from sensory data. So accelerometers and gyroscopes are very popular among people out here. I think every team is using it in some shape or form. What if I tell you that you can actually detect speech from accelerometer? Now, you will find it hard to believe, but a group out of Stanford has just shown that. Magic of machine learning, some understanding of the underlying physics. They can infer gender, they can infer speaker, they can infer if there are known text or words that you are seeking. Or what if I told you that if you share the charge level of your battery on your phone to an application, I can tell where your location. Now, the magic out here is, besides machine learning, there's a lot of side information available. Google very conveniently makes maps available. So the degree to which adversaries have access to machine learning and data has increased tremendously, and along with it, the ability to make inferences. So for example, the same group at Stanford again showed that apps which have access to this kind of data, which basically is on every phone, because that's unprivileged information in these devices, coupled with mapping information and some prior training, they can basically infer your daily trajectory at a pretty rapid rate. So these are the kind of risks. Some work out of my group. You share barometer data, who would know that now barometer reveals height combined with topographic maps. We can trace you through at least interesting terrains like LA where there are hills and stuff like that. Will not work in Memphis maybe, but works here. Okay, so another challenge is implications for third parties. These sensors often are non-specific. So I recall an incident meeting a year ago where some researchers were roaming around with cameras, and the idea was they're trying to learn something about themselves. The problem was it was catching images and audio snippets of everyone around them. And their reaction to request to stop it was initially rather adversarial, but eventually they consented. The point is, these things are creepy or viewed as creepy by many. And I think you cannot ignore the concerns of these second and third parties as you go around designing these systems. At the very least, there should be a very visible notification, and then of course some way of opting out if needed. And again, there are technologies emerging. Key point I would like to make is that the standard thing that we are used to, anonymization, strip name, and other kind of PIIs, is insufficient. In fact, Cynthia Dork at Microsoft, a leading privacy researcher, said anonymized data it's not data. Okay, I mean these by the time you are done removing every trace of identity, you are going to be left with nothing. So that's not possible. So when it comes to defending against these things, of course, seeking user permission, reducing sensor data quality, these are kind of two standard techniques. What's also additional things, warn about risky usage pattern. A challenge with these sensors is their risks are very hard to understand, hard to articulate, and therefore exposing them to users in an understandable fashion is important. So instead of simply saying we are collecting accelerometer and gyrometer data, I think you need to go a step further. And by the way, what kind of inferences are known to be possible? Okay, otherwise, I think most non-computer scientists would have a hard time kind of understanding what risks they are undertaking by agreeing to this. As a strategy, share inferences, not raw data, which means even when you're collecting from the participants, don't do a data grab. There is no need to get raw sensor data. Phones are capable of lots of computation. Minimize the data, so I take away features or take away the eventual answers. So that's kind of the second part of a good system design. And then finally, deploy mechanisms which at a fine-grained level perhaps play this privacy utility kind of a trade-off that maybe you may have to sacrifice on the utility a bit in some cases to maintain privacy, or kind of vice versa, by selectively transforming or messing with the information. So this privacy problem is not just one of keeping identity private or data encrypted. It's really about making sure that the data that you are choosing to share, you have some control over what is inferable from it and what is not, and exercising control over that process. And that's something which sort of people in database communities are looking. So there is this theory of differential privacy which has emerged, which basically says the assurance you can give to your participant is that whether you choose to participate in my study or not, it's not going to make any difference. By choosing to participate, you are not revealing anything more, and the magic out here is you're hiding behind the crowd. So these are studies where everyone contributes data, and then there are so-called aggregation type computation you're performing. Now, of course, that doesn't work for one-on-one kind of thing. If there is a CHF patient and you're providing care for him, then of course identity is known, and so you cannot hide behind the crowd, and in which case you really need to sort of think more carefully about how to organize the sensor data flow. So one of the concepts is that could we mess with the sensor data prior to sharing, much like firewalls do or kind of a gate does, essentially protect the leakage of information so that you can reveal to the user and kind of let him or her control as to what inferences can be made or not made, kind of a whitelist or blacklist of possible uses out of this data. So some work that Santosh and I have been doing, it kind of realizing these kind of concepts, but there is other activities as well. So some of the observations privacy concerns are real. Some of the studies we have done clearly show that once we reveal to them the real implications of the type of data they are sharing, the privacy concerns naturally go up. So ignorance is bliss, but this level of ignorance is certainly going down. And if not sort of taken care of, this can hinder adoption over time. Value proposition is often unclear. So you're asking for all this data, what am I getting? So unless that is made clear, which in case of health, I guess is often a strong case, but needs to be very obvious. One thing which may help or hurt is expectations of privacy change over time, and it could go either way. Sometimes we get used to a technology and kind of things which we deemed private, we don't, and of course things can go the other way also. So that's hard to predict. Privacy protections in current sensing systems are pretty meager, and the third-party privacy concerns are extremely important. Closing, one of the things that I would just highlight is this, among the many principles, I think one, if I were to highlight, is this principle of least privilege. Don't ask for information or resources that you don't need. Okay, so this is kind of the classic data grab types of situation. Avoid that. So it leads to a system which is more robust. So for example, let's say you're doing an mHealth app. You could design it by sending ECG data and GSR data and audio data and then kind of do the stress inferencing at your end. The problem is with these things, like Santosh's work has shown, you can detect episodes of taking cocaine and things like that. Well, can certainly be an issue. An intermediate solution, compute some of the features like heart rate variability, send those out. Still risky. If you can, compute the stress value on the device and only share that. And I guess the final sort of thing is the whole notion of currently the way we these things. I think informed consent upfront is, to me, essentially misleading the participants. Okay, it's wholly inadequate, and I think unfortunately until IRB is actually beginning to have computer scientists, these things are not going to get fixed. The risks from high dimensional sensor data are just way too much. Perhaps more detailed consent, but that would be burdensome. Some sort of continual fine-grained consent, burdensome. There are alternative theories of privacy. So Helen Nessenbaum at NYU, for example, has this theory called contextual integrity model, which basically says that people feel violated in privacy when it differs from the social norms they expect, and perhaps finding these legal and social norms and encoding them into the software might be the approach to go. So this is kind of fluid area of sort of research. Making privacy usable is extremely important.